All right, y'all, we're going to do some parametric equations today, and we're going to focus in on doing this with Desmos and then creating an equation that combines our parametric equations. So let's go and get started. Chelsea is launching her friend John in the air with a human catapult to a bounce pad in the center of the lake. The catapult is stationed on a cliff that is 50 meters high. Chelsea sets the catapult to 40 degrees and determines the catapult launches at a speed of 35 meters per second. The edge of the lake is 116 meters away, and the center is 215 meters from the cliff's edge. Sketch a picture. All right, so let's do a quick picture on this just so we understand what is happening. So first things first, we've got a cliff. And out there in the middle of nowhere, we've got a lake out here, okay? And what it tells us is that to that lake is 168 meters. So this is about 168 meters. And in the middle of that lake, we are about 215 meters away, and it just keeps going. Now, at that point, we also have Chelsea, who's up there having some fun with her friend John, and John is getting ready to get catapulted out, and he is going to, hopefully, if everything works good, land somewhere in that water. Now, we have a horizontal component when we get shot into the air at a certain angle. So this angle, we have the horizontal will be at 40 degrees. And then we also have a vertical component when we do these. So there's our horizontal component X, and this is going to be our vertical component Y. And somewhere out there on top of this 50-meter cliff, John is going to get shot off and land in the water. So let's write a couple of equations. I've written the setup for equations up at the top. So the horizontal component is going to be straightforward. We just read it the way it is. The horizontal component will be X equals to VO, which is our initial velocity. And our initial velocity is 35 meters per second. So I'm going to write 35 cosine of the angle. So cosine of the angle. And our angle is at 40 degrees. And then we're going to put T, which is going to be our variable, which is time. So now the distance away, which is X, our horizontal component, their distance out is going to be modeled by that equation. So now let's go ahead and write our vertical component, which is going to be Y. So Y equals 2. Now, we do have to remember that this is -1/2 G, and that G is gravity. So we are talking about meters. So gravity is 9.8 meters per second squared. So we have to cut that in half. And half of 9.8 is 4.9. So I'm going to write -4.9 T squared plus the initial velocity again, which is 35 meters per second. So 35 cosine of the angle, or I'm sorry, sine of the angle. Okay, so 35 sine of the angle. Plus the initial height, which is what H stands for, initial height, which is a 50-meter cliff. Okay, so from here, let's go ahead. We've got our sketch. We've got our parametric equations. We're going to go to Desmos, and we are going to type this in. So let's go in here. We start by making a point. And how we do that is we just go with our initial velocity, our angle, and our T. So 35 and 40. So I'm going to write 35 cosine of 40 with a T attached to it on the outside of the parentheses. Super important. You don't want to put that in there. I'm going to put a comma. Now that's going to give us our X component in this coordinate point that's getting ready to be graphed. Then what I'm going to do is I'm going to put the rest of the equation in. And remember, we have sine, not cosine, so sine. So -4.9, 35, 50. So let's go here. Let's type that in. So -4.9 T squared plus, keep typing that in, 35 sine of 40t. And then plus the initial height, which is 50. So let's go back here. Let's make sure I put that T on that equation. And what we're going to do is we're going to focus in on getting this graph into Desmos. So with that being said, you're going to look at it, you're going to say, well, do I see much of anything? Well, I know the initial height is 50. It looks like it's going out, and then it just stops. Well, part of the reason why it stops right now is that our T value isn't far enough out there. So maybe we're going to go ahead and estimate. Maybe it takes 4 seconds We're getting pretty close. Let's go ahead and maybe it takes 6 seconds. We're pretty close. I'm just going to go ahead and guess and say, let's take 8 seconds, give it a little bit longer whatsoever. The other thing we want to pay attention to is we need to make sure we are in degree mode, because you'll see the graph changes if you're not. So we are in degree mode now. And we have a graph. Now, the thing with Desmos is when you're messing with this graph, it's not going to let you trace it. Okay, and that's a real problem. So there's some ways around that. So let's go ahead and come up with that way around it. The first thing I like to do is put a slider on. So if I press T and maybe another variable, it'll add a slider. I'm going to add a T slider, and I'm going to shut off this graph. Now, the problem with this is you'll notice that the graph goes away. So what I like to do is I kind of like to think about this in terms of like, well, what is happening with this graph? So I'm going to go ahead in my brain. I'm going to go, there it is, and it lands somewhere around there. And I'm going to show you how to deal with that again at the end of this, or closer to the end of this. So now what I'm going to do is I'm going to go back to my T slider, okay? And I am going to start my time at 0 seconds. I'm going to go out for about 8 seconds. And then what I'm going to do is I'm going to make my T step very small, so 0.001, and that'll give me a really pretty good graph. At this point, I can go ahead and I can actually see the motion of John as he's flying through the air. Oh my goodness. And if we remember, the edge of that lake is only 168 meters out there. And if we follow this out, oh my goodness, we have some real issue right here. We have a real close call right here. John may not be making it. So anyways, let's go ahead, and what I'm going to do is I'm going to add on some other things to this graph just so I can see a little bit better. Okay, so I like to copy the first equation, type in x equals, and then I like to paste it. It starts giving me measurements and calculations that I can see easily. Control C, and then I'm going to type in y equals to and Control V. It allows me to make those calculations as I trace along. It'll give me the x and the y values you can see there, or I can even add a label and it will do that as well. Okay, this is just one great way of seeing what is taking place. And if we trace it down, we can actually see that maybe John's really, if we get there, it really not, John may not make it. I'm not sure. Sorry, John. May not actually make it in there. It looks like maybe at that point, we've got 167 meters. So what we want to do is, as we're doing this, we want to pay attention to what x meant and y meant. So x, if you remember, simply meant the distance away from the cliff. So x equals distance away from the cliff. Okay, and then also what we need to do is pay attention to what y meant, right? Y is the height of John. Okay, so it is the height of John's motion. And you'll notice x is distance, y is height. Well, where do we find the time? Because we have a third variable. This is our when, our time. Okay, so when we're looking at this first question here, it's going to simply say, okay, well, let's get down here. When and where will John land? We're making an approximation right now. So when and where will he land? Well, if I trace this out, right, John comes down, and it looks like he lands right about here. Okay, we can just keep going closer and closer and closer. But the problem is we're only making approximations at this point. It looks like he lands somewhere around 167 feet away. So maybe 167 feet away. And it happens at 6.24 seconds. So let's come back here. So class kick, it looks like time equals to 6.24. And he's roughly about 167 meters away. Well, we've got a real problem for John because that lake's edge starts right there. So really what it looks like is John may actually not be making it, okay? Sorry, John. But let's go ahead and let's get more of a precise calculation because who knows, maybe John just does barely make this situation, okay? So it says, what equation can be used to model the flight? So let's go back to Desmos, and I'm going to erase what we have here. And let's go ahead and build the equation. So we have to remember that the first equation was x equals to 35 cosine of 40t, and y is equal to negative 4.9 t squared plus 35 sine 40 t plus 50. Okay, so those are our equations. Okay, notice they both have t in common. So what we're going to do is solve for t in the most simple equation we have. Well, what's the most simple equation that we have? It's our x equation. So what I'm going to do is I'm going to solve for t, which means I'm just going to divide by 35 cosine of 40 on both sides. And when I do that, we get this equation that looks like t equals to x over 35 cosine of 40. Okay. All right. So now what do we do with that? We take that t and we stick it right into the next equation, into our y equation. Okay. So let's do that now. I'm going to write y equals to negative 4.9 x over 35 cosine of 40 squared plus 35 sine of 40. But now where t is at, I'm going to put this x over 35 cosine. So x over 35 cosine of 40. Oops. Sorry. X over 35 cosine of 40 t plus 50 on the end, okay? Now, we're going to clean it up just a little bit. So I'm going to write it out one more time. Y equals negative 4.9 x over 35 cosine of 40 squared plus 35. Now notice what happens with those 35s. There is a 35 on the top. Whoops. There is a 35 on the top. And there is a 35 on the bottom. It cancels out. There is a sine 40 on the top and a cosine 40 on the bottom. Well, what is sine over cosine? That is tangent. So that becomes tangent of 40 x. Okay, and then we have plus 50 on the end, the initial height. So let's go and let's type that in real quick. Okay, so I'm going to come over here. I'm going to type it in. Y equals negative 4.9. Put in that fraction, x over 35 cosine of 40. And then I'm going to square it plus tangent of 40 with an x. And then I'm going to put plus 50 on there. Okay. We can see all of that stuff, and you can see actually the graph works out. So now, just to make sure I did this right, I'm going to press trace. And what it does, it allows me to follow that path. What it also allows me to do is actually click on the graph. So now I can actually come in here, I can click on the graph and I can say, check it out. 167 is where John actually lands. So John actually lands at 167.02. Sorry, John, you didn't make the edge of the lake, but it is, you're pretty daggone close. Got a little excited there for a second, okay? And the question is, like, when does he hit it? So this is where he hits. So he hits the ground at 167, hits ground. And when is that? Okay, well, there's another way we can find when. What I'm going to do is I'm going to come up here and I'm going to turn off the slider. Check this out. And when I turn off the slider, it allows me to graph the time graph. And when we graph the time graph, notice, we can verify this. Check this out. There's 75.8. And then up here on the green would be 75.8, okay? 75.8, 75.8. But if I want to find out the time, all I got to do is look at this purple graph and I can say, well, he hits the ground at 6.22 seconds, okay? So this is showing us time. And over here, this is showing us exactly when, or I'm sorry, not when, but exactly where he hits the ground in relation to the cliff. All right, y'all, I hope that kind of helps you out. Y'all have a great day and enjoy some parametric equations.